Welcome to qnawire.
Problem 128 asks to find the centroid of the volume of a sine curve rotated about the x-axis, described by the equation shown where y equals b sine pi x over 2a. And through symmetry, we can already see that the centroid in the y and z direction are both equal to 0. So now we're left with finding the centroid in the x direction. And to do that, we'll use the equation where the centroid in the x direction times the total volume is equal to the integral of the centroid's differential element. And that differential element is going to be a disk integrated throughout this volume. And so let's first find the volume that we need for this equation, which is equal to the integral dv. And that differential volume is going to be equal to pi r squared, the area of a circle, times the change in x as we move along this volume in the along the x-axis. However, we don't know what r is, so we'll have to substitute in for r. And we can do that using the equation of the line, because we know that the radius will be along the is parallel to the y-axis. We can plug in the radius for y at any point along this volume. So plugging in the radius for y into the equation of the line, we have the radius is equal to b sine pi times x over 2a. And then we can plug that back into our differential volume and square everything. Now we can find the volume. And plug in the differential volume. Solving the integral, we get pi b squared times x over 2 minus sine pi times x over 2a divided by 2 times pi over a. This is all from 0 to 2a, which I should have mentioned earlier, but that's where we're integrating along the whole length of this volume, as shown in the diagram. And so plugging in 0 and 2a, we get that the volume of this object comes out to 1/2 pi times a times b squared. And now we need to find the right side of our centroid equation, which is the integral of the differential element dv. This will also be integrated from 0 to 2a along the whole volume. And we can plug in x for the centroid of each differential element, because it changes along with the each x value along the x-axis. We already found dv, so we can just plug that in. And to solve this, we'll have to use integration by parts. Now we can plug our parts back in. And start off with u times v for the integration of parts. That's how it goes. And then you subtract the integral of v du for integration of parts. So then solving the integral, it comes out to pi b squared times (2a times 2a over 2 minus a times a over 2 minus 1/4 x squared plus a squared over 2 pi squared times cosine pi x over a from 0 to 2a for that last part. So plugging in 2a and a, we get that the integral of the differential element is equal to 0.6487 pi a squared b squared. And now we know enough to solve our original equation for the centroid, which was the centroid times the total volume is equal to the integral of the differential element So plugging in the volume that we found for the left side of this equation, we can then set it equal to the differential element on the right side of the equation.